Hi, everybody. It's Professor Mitchell. We're continuing Chapter 3 on numeration systems and whole number operations. And today we're going to be talking about Section 3.4 on multiplication of whole numbers. In this section, we'll talk about multiplication through various models, properties of multiplication and how to use them to develop computational strategies, multiplication algorithms, including the standard algorithm, and how to use them to solve problems, multiplication with number bases other than 10, and mental multiplication skills and estimation techniques. Multiplication of whole numbers can be modeled in several different ways. We have the repeated addition model, where multiplication can be thought of as repeatedly adding the multiplicand n times, where n is the multiplier, and we'll see an example of that in a little bit. The array and area models, multiplication can be visualized by constructing an array of crossed sticks or a grid and counting intersection points or grid components. And we have the Cartesian-Product Model, where multiplication can be thought of in terms of Cartesian products of sets. In the repeated addition model, if we have 4 groups of 3 brushes, we can use addition to put the groups together. When we put equal size groups together, we can use multiplication. We can think of this as combining 4 sets of 3 objects into a single set. So instead of writing 3 plus 3 plus 3 plus 3, you can just write 4 plus 3. Here are a couple of other ways of illustrating the repeated addition model. 5 times 4 can be illustrated with 5 sets of blocks, each of size 4. Or you can use a number line model. So remember when we talked about addition, the way to illustrate 4 plus 4 plus 4 plus 4 plus 4 would be like this with the blue arrows. And that's the same thing as 5 times 4. The definition of multiplication of whole numbers: for any whole numbers a and natural number n times a is just defined to be a plus a plus a, plus a, n times. There are n terms here. So here's what the array and area models look like. 2 different illustrations of 4 times 5. So if you put 4 sticks going this way and cross them with 5 sticks, you get a total of 20 intersection points. You can also use a grid model to illustrate it using area. If this side has length 4 and this side has length 5, then you would have a total of 20 squares in your grid. For the Cartesian product model, suppose you plan to take 2 web-based courses at your local college. You can take one of the following: world history or ancient history for your first course, and for your second course, you can take either Latin, French, or German. To show the number of different schedules you could have, you could use a tree diagram. The ways of designing your schedule are a result of selecting a history course from the set H, which has 2 elements, world history and ancient history, and a foreign language from the set L, whose elements are Latin, French, and German. So here's what your tree diagram looks like. All right, this is illustrating the Cartesian product H cross L. So first pick your first course, world history or ancient history. And then, regardless of which course you picked first, you can pick either Latin, German, or French. So notice that you come up with a total of 6 different schedules. The fundamental counting principle tells us that the number of ordered pairs in the Cartesian product of H and L is 2 times 3, which is 6. The definition of multiplication using the Cartesian product model says for finite sets A and B, if the number of elements in set A is A and the number of elements in set B is B, then A times B is defined to be the number of elements in the Cartesian product of A and B. In this alternate definition, sets A and B do not have to be disjoint. the expression A times B, or simply AB, is the product of A and B. A and B are called the factors. Multiplication of whole numbers is closed, just like addition was and subtraction was not. If A and B are whole numbers, then A times B is a unique whole number. Multiplication is commutative. If A and B are any whole numbers, then A times B and B times A are the same thing. Multiplication of whole numbers is associative. If A, B, and C are whole numbers, then the product of A times B and C is the same as the product of A and B times C. And then multiplication of whole numbers has an identity element, which is the number 1. So remember when we talked about addition of whole numbers, we called 0 the identity element for addition, because when you add 0 to any number, you get the same number back. The same thing happens when you multiply a number by 1. There is a unique whole number 1, such that for any whole number A times 1 and 1 times A both just come out to A. Now 0 does have a special property with multiplication. There's nothing like this with addition. For any whole number A times 0 and 0 times A always comes out to 0. Here's an illustration of the commutative property of multiplication using the area model. 3 times 5 is clearly the same thing as 5 times 3 if you just took this figure and rotated it 90 degrees. This is kind of neat. I'd never seen anything like this before. They're using blocks to illustrate the associative property of multiplication. So why don't we start here? Imagine this thing is all stuck together. And at first you slice it into 3 pieces horizontally. So you have 3, let's call them flats, each of which has an area 5 times 4. See that here. So this is an illustration of 3 times the product of 5 and 4, because each one of these is 5 times 4, and there are 3 of them. However, if you took the same figure and sliced it up vertically, then you have 4 flats, each of which has an area 3 times 5. So that's an illustration of the product of 3 times 5 and 4. Multiplication, the distributive property of multiplication over addition. We've never talked about this before because we're just now getting to multiplication. The area of the large rectangle that you see here equals the sum of the areas of the 2 smaller rectangles here and here. See, this rectangle is this one right here to the left of the dark line. And this rectangle over here is the one to the right of the dark line. So over here you have an illustration of 5 times the sum of 3 and 4. And that's the same thing as 5 times 3 plus 5 times 4. So you've all seen the distributive property before for any whole numbers A, B, and C. The product of A and B plus C is equal to AB plus AC. Distributive property also works over subtraction for any whole numbers A, B, and C. With B greater than C, remember that we're dealing in whole numbers, so B minus C is only defined if B is bigger than C. A times B minus C is equal to AB minus AC. Because the commutative property of multiplication of whole numbers holds, the distributive property of multiplication over addition can be rewritten like this. So we can multiply on the right side, and that would give you B times A plus C times A. The distributive property can also be generalized to any finite number of terms. For example, A times B plus C plus D would give you AB plus AC plus AD. when the distributive property is used to write a times b plus a times c equals a times b plus c, that's called factoring. So for example, in our Math C course at Merced College, intermediate algebra, that's one of the very first things we talk about in that course. The factors of AB plus AC are A and B plus C. So now we'll use an area model to show that x plus y times z plus w is equal to xz plus xw plus yz plus yw. If you remember from your algebra classes, FOIL, first, outer, inner, last, that's where this comes from. So here's the area model. All right, we have a rectangle whose width is x plus y and whose length is z plus w. If we cut that rectangle into 4 pieces, the areas of those 4 pieces are xz, xw, yz, and yw. Use the distributive property of multiplication over addition to show the same thing. All right, so what's happening here, let me get out my pen, is that we're taking x plus y and we're distributing it here and here. So that's how they came up with x plus y times z and x plus y times w. And now we're going to take the z and the w, and we're going to distribute them. And that's going to give you the thing that we were looking for. All right. We've seen this, I think, 2 or 3 times before, the definition of a to the n. If a, the base, and n, the exponent, are whole numbers and n does not equal 0, then a to the n is defined to be a times a times a, et cetera, n times, and a to the first power is just a. A to the 0 power also means something, but you can't really demonstrate it using repeated multiplication. Notice that exponents were kind of invented to deal with repeated multiplication, just like multiplication was invented to deal with repeated addition. So there's kind of a nice parallel between those two things. All right, some properties of exponents. For any whole number a and natural numbers m and n, the product of these powers is equal to, let's see, well, a to the m times a to the n is equal to a to the m plus n. To multiply powers, you add exponents. Okay, to multiply powers, you add exponents. And for any whole number a and natural numbers m and n, a to the m raised to the power n is equal to a to the m times n. So in a beginning algebra course, this is called the product rule for exponents, and this is called the power rule. All right, for any whole number a and natural numbers m and n, a to the n times b to the n is just ab to the power n. And if a, m, and n are natural numbers with m greater than n, then a to the m divided by a to the n is a to the m minus n. So remember, back on the previous slide, we said to multiply powers, you add exponents. To divide powers, you subtract exponents. So that makes a lot of sense. All right, so in this example, we're going to write each of the following with only one exponent, starting with 2 to the 6th power times 8 to the 5th power times 16 to the 3rd power. Notice that 2, 8, and 16 are all powers of 2. So that's how we're going to do this. We're going to rewrite 8 as 2 to the 3rd. We're going to rewrite 16 as 2 to the 4th. And now we're going to use our properties of exponents. First of all, to say that 2 to the 3rd raised to the power 5 is 2 to the 15th. That's the power rule. And 2 to the 4th to the power 3 is 2 to the 12th, also the power rule. And now we'll use the product rule to say that when you multiply all these powers of 2, you get 2 to the power 6 plus 15 plus 12, which is 2 to the 33rd power. All right, some multiplication algorithms. Here we're illustrating 13 times 3 using longs and units. So here, let's say at the bottom, we have a model of 13, 1 long and 3 units. So if we make 3 copies of that, that's illustrating times 3. Notice that we have 3 longs, which is equal to 30, and we have 9 units, which is equal to 9. So what you have here is 9 plus 30, which is 39. All right, multiplication by powers of 10. To multiply by 10, replace each piece, and when we say piece, we're talking units, longs, flats, and blocks. Replace each piece with a base 10 piece that represents the next higher power of 10. In other words, replace each unit with a long and replace each long with a flat. And I guess if you needed to, you could replace each flat with a block. All right, so for example, to illustrate 23 times 10, we'll replace these 2 longs with flats, and we'll replace the units with longs. Remember, each of these represents 100, and each of these represents 10, so that gives you 230. Multiplication using expanded addition. So remember that you can write a number like 367 as 3 times 10 squared plus 6 times 10 plus 7. So now we'll use the distributive property. Let's see, where did my pen go? We'll use the distributive property to multiply this by 4 and multiply this by 4 and multiply this by 4. So that gives you 4 times 3 times 10 squared plus 4 times 6 times 10 plus 4 times 7. Now we'll use the associative property to put 4 times 3 together. It's easy to see that 12 times 100 is 1200. It's easy to see that 24 times 10 is 240. And of course, 4 times 7 is 28. That gives you a total of 1,468. Multiplication with 2-digit factors. All right, bear with me here for a second. So we're modeling 23 times 14. Going across here is 23. We have 2 flats and 3, actually, sorry, no, think of this as, let me get my pen back here. It would not be flats and longs. It would just be, just imagine this these 2 longs here that I'm drawing lines through, and then these 3 units. And when you multiply that by 14, it means you're making 14 copies. So here's 10 copies, and here's 4 more copies. So if you kind of group these together, here's 20 times 10, which is 200. Here's 3 times 10, which is 30. Here's 20 times 4, which is 80. And then 4 times 3 is 12. So that gives you 322. Oops. All right, lattice multiplication. I enjoyed lattice addition and I enjoy lattice multiplication. So let me show you how to set this up. You draw this diagram, which is called a lattice. And across, let's say the top, of the diagram, you write one of your numbers, doesn't matter which one. And then down the side of your diagram, you write the other number. And then what you do is you go 1 times 2 is 2. That's how they got 0, 2 here. 4 times 2 is 8. That's how they got 0, 8. 1 times 3 is 3. And 4 times 3 is 12. And now to get our product, we're going to add going diagonally. So here there's just the number 2, which gives you 2. And then going down this way, 8, 1, and 3 add up to 12. So you put a 2 here and carry a 1. And then 1 plus 2 plus 0 is 3. And that's it. So the answer is 322. All right, base 5. So here is our, actually I almost said remember, but we've never used this before, the base 5 multiplication table. So again, think about pennies and nickels. First of all, anything times 0 is 0, just like in base 10. Anything times 1 is itself, just like in base 10. So now let's talk about this part of the table down here. That's really the only place where we really have to do a lot of thinking. 2 times 2 would be 4, as in 4 pennies. 2 times 3 pennies would be 6 pennies, but remember there's no such thing as the number 6, or at least not the digit 6 in base 5. So if you had 6 pennies, you would regroup those as a nickel and a penny. So in base 5, we write the number 6 as 1, 1. 2 times 4 pennies would be 8 pennies, and you would regroup those into a nickel and 3 pennies. 3 times 2 is the same as 2 times 3. 3 times 3 pennies would be 9 pennies, which is a nickel and 4 pennies. 3 times 4 pennies would be 12 pennies. 12 pennies can be grouped into 2 nickels and 2 pennies. That's how you get 2, 2. Uh-oh. Hang on, lost my mouse. Okay. 4 times 2 is the same as 2 times 4. 4 times 3 is the same as 3 times 4, and that brings us to 4 times 4. 4 times 4 pennies would be 16 pennies, which can be grouped into 3 nickels and a penny. That's how you get 3, 1. Okay, so let's see. How are we going to use that? We're going to do 2, 1 times 3 in base 5. All right, so let's group 2, 1 into 2, 0 plus 1. 1 times 3 is 3. And then 2, 0 times 3 would be 1, 1, 0, because remember that in base 5, 2 times 3 is equal to 1, 1, right? That's from our table. All right, so that comes out to 113 in base 5. Let me just get my text out of there. And here they're showing it to you using the standard algorithm. 1 times 3 is 3, and then put in your placeholder 0. 3 times 2 is 1, 1. So you add those together, and you get the 2, 1 times 3 in base 5 is 1, 1, 3. All right, little base 2. So remember in base 2, the only digits are 0 and 1. So this shouldn't be too hard. All right, 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. And then going over here, it's the same thing. So if you wanted to, you could put a placeholder 0 right here. And you get that other 1, 0, 1. And then if you just add going down, it turns out that 1, 0, 1 times 1, 1 in base 2 comes out to 1, 1, 1, 1. All right, mental mathematics for multiplication. There's front-end multiplying. So for example, to do 78 times 4, you can split that up into 70 and 8. 70 times 4 is 280, 8 times 4 is 32, and then you just add those together. This is something that I find myself using sometimes. I am so lazy. I know I walk around with a calculator in my pocket just like everybody else, but I am so lazy that I would literally rather try to find a way to do it this way than have to reach into my pocket and get my calculator. I'm not lazy. All right. Using compatible numbers, if you had to do 2 times 8 times 5 times 40 times 5, look for numbers that you can pair together that give you nice answers like 10 and 200. So if you happen to notice that 2 times 5 is 10 and 40 times 5 is 200, then you can just do 10 times 200 is 2,000. 2,000 times 8 is 16,000. It's always helpful to think of things in terms of money. Everybody understands money. All right. So for example, when you're multiplying by 25, think of the product of 84 times 25 as 84 quarters. So 84 quarters is equal to $21, and then you just have to remember to change that to 2,100 cents. And then to estimate the product, if you don't need the exact answer, 474 times 9, just do 400 times 9, which is 3,600, and then do 70 times 9, which is 630. The 4 at the end is really not that important, so this will get you pretty close to the answer. What we're basically doing here is rounding the 474 to 470. And that's going to do it for section 3-4. One more section to go and we'll be done with chapter 3.